Hello, in this video I will show you how to perform PCA, principal component analysis, using the R package prcomp with a synthetic dataset. Okay. Before we start, let me just provide you with a list of key points about PCA. PCA is a dimensional reduction method. It is unsupervised learning, and it's for discovering the hidden structures of the observed data. And the principal components are linear combinations of the original variables. Also, the R package prcomp uses something called singular value decomposition, which leads to orthogonal or we say independent principal components. It does not allow other types of rotation such as oblique. And also for dimensional reduction, we need to select the first few important principal components, and usually there's three methods. One is just select those PCs whose eigenvalues is greater than 1.0, or if we plot out explain the variance ratio, and if there's an elbow pattern, we can select those PC before the turning point. I'm going to show you a PC plot later and explain more about this method. Third method, we can just select those PCs whose accumulative explained variance is larger than 90%. Okay, now let's start the R demonstration. We set random seed. I like to use the current date as the random seed. Sample size 100, feature 10. We're generating a random matrix by drawing random samples from the standard normal distribution. So we're not incorporating any correlations among these features, so probably we will not see much hidden structure of the data. Okay. Assign feature variable names, feature 1 to 10. Okay, now to perform the PCA using this R package, the syntax is relatively simple. So put the data matrix in there, scale dot equal to true, meaning we're going to scale the standard deviation to be 1. Centering equal to true, that means we're going to center the data to have mean 0. Okay, so basically we're doing a standardization of the data, and then we can just run prcomp. It will generate the object PCA. A quick look at this object. It provides all the PCs, PC10. You get as many as features. So get 10 features, you get 10 PCs. Okay, and you can see standard deviation, that's the square root of the eigenvalue, also equal to the variance explained. By that, the square root of the variance explained. So you can see from PC1 to PC10, the standard deviation is decreasing. Okay, proportion of variance, that's important. So you can see the principal component 1 explained 14% of the variance, and PC2 explained 12.9%, etc., etc. And the third row you can see is the cumulative explained explained variance proportion, and you can see when we reach PC9, it went over 90%. So this is really a not very well structured data set. Okay, so let's do some visualization of the result. We can plot out this explain the variance ratio. You can see it keep going down at each PCs. So it does not show an elbow pattern, which is it will go flat after one principal component. So this is what this plot is saying, and we don't see an elbow pattern here. The next visualization, which is important one, is the biplot. It is the plot you plot all the original observations against the first two principal components. Okay, and you can see there's also feature vectors. So it's going from the origin all the way to different features with an arrow, and it shows you how closely related these features to PC1 and PC2. Okay, so if the arrow vector going toward the PC, it's more related to that PC, and the length of that arrow indicates strength. Okay, and also the angle between two feature vectors indicate how correlated those two features are. Okay, for example, here you can see feature 9 is related to PC1, and it's not a weak relationship, but feature 9 and feature 3, they have a wide angle between their feature vectors, so these two are not very related. And also, this allows you to see, to visualize the clustering of the original data points, and also allows you, sometimes you can spot some outliers. If, for example, this one, like 84, it may not be an extreme outlier, but it's kind of outside of the main cluster of the data points. Okay, so you can read a lot of information from the biplot. Okay, all right. The next result is provided by prcomp in R is we can look at the rotation matrix. Okay, so the rotation matrix is actually we talk about PCs are linear combinations of the features. So this rotation object is really the provided the coefficient of the linear combinations, or sometimes we call them loading coefficient, loading factors. Okay, and these can provide certain information. For example, the magnitude of feature of these, this coefficient can let us have an idea about how important this feature is toward that principal component. For example, in this case, the feature 1 is loaded negatively, so it's actually negatively loaded on the PC1, and it's a relatively important one, large contribution to PC1, but feature 2 is negatively contributed to PC1, but this is 0.01, so it's a very small loading. Okay, and if you go through all 10 features, you can actually sometimes will see, say, feature 5 and 6 and 7, they are like, or even 8, 9, they are like more loaded together onto PC1. And these are sometimes really useful information for you to have a better understanding of the principal components, may give you some interpretability. For example, maybe some variables, some features cluster together and loaded positively on the PC, but some other features are loaded collectively, negatively loaded on the PC, things like that. So they form a contrast. Okay, the next one we can talk about is the PCA scores. So we can look at that. This one is actually, let's look at the dimension. It's 100 by 10. This is the relationship between the original observation with the PCs. So this allows you, this gives you the same information as the biplot. So you can see the first observation, is how it's related to all these principal components, the magnitude, the direction will give you more information about how these raw data is related to the principal components. Okay, and so this is a 100 by 10 matrix, so it's very large. So we don't go over the entire matrix here. Another important component is eigenvalues. So this is the square of the standard deviation, and from that we can get the proportion explained by that principal component. So we can plot out this graph, which is the same plot we generated before. So just these plot make you understand how this plot is made. Okay, so it's really the proportional variance explained. Okay, I think we're running out of time. So this is the one method we can use the number of principal components selected by using the accumulative explained variance. So in this data set, when we calculate accumulative proportion variance greater than 90%, we got the first 9 component principles, the principal components, and we only got 10, so we have to go all the way up to 9. So it's not much of a dimension reduction here, and this is expected because we generate the data set totally, the features are not related. Okay, so I hope this is a good introduction for principal component analysis using the RPAC, the prcomp, and you have seen that this is a very simple implementation of the PCA, and we could not do the other rotations, and there are other more complicated features or more sophisticated information we extract from a PCA, but we have to find other R packages. Okay, thanks for watching.